All right, folks, this is our video for lecture 5.2, day number 1, volumes by cross-section. And if you're wondering why I have all of this drawn out and written out already before we even start, it's because I just did this entire video without the microphone on. So I guess I'm going to roll through what I already have written down here. I've erased some of the arithmetic, and we'll do that again together. Here we go. So we're going to talk about volumes by cross-section. So consider the following blob over here, this guy, blah, blah, blah. And suppose we wish to find the volume of this solid. To do this, we need a frame of reference to make measurements. So let's impose an XY axis. Shebang. There we go. Boom. And even though the blob is 3D, you can tell it's 3D by my lovely rendering and its cross wire frames there. Even though the blob is a 3D volume, we will use two-dimensional axes to measure our volume. The next thing that we're going to do is we're going to subdivide or cut the volume into n slabs. So just like when you have a curve f of x and you want to find the area underneath that curve, you start by cutting it up into n equal little rectangles, and then you start doing an approximation. We're going to do the exact same thing here, but we're going to cut it into n slices or slabs. So since we have a 2D axis, we have two possible directions that we can slice up the volume. We can either slice it perpendicular to the x-axis, or we can slice it perpendicular to the y-axis. So we'll take a look at that as we go. Now, if we do actually slice the volume perpendicular to the x-axis, this is what we're going to get. Here's my lovely little diagrams. And we start off here, and then in this case I'll just choose, I should say not 4 slices, because there's 5 slices of bread, right? But there's 4 cuts. And those 4 cuts are going to generate these 5 sub-volumes. And what we're going to do is we're going to estimate the total volume by approximating each sub-volume by an approximating cylindrical slab. So let me highlight that. Oh, what the heck happened there? That's not what I wanted to do. We're going to approximate each one by using a cylindrical slab. Now, what do I mean by cylinder? Well, when you say cylinder to most people, they think of soda can or whatever. But actually, a cylinder is anything that has the same base at the top of the bottom and these rulings from side to side. So it can be any shape. What you're thinking of when you're thinking of soda can is what's called a right circular cylinder. But the nice thing about the cylinder is it's easy to calculate its volume. So now let's consider a typical slab out of the middle here. I'm just going to grab this middle slab. This little T-bone steak. So here's my general ith slab out of the middle. And each slab, if we cut this into n equal slices here, each slab, even though I haven't really drawn it that way, each slab is going to have the same width of, since we cut this perpendicular to the x-axis, they're each going to have a width of what we usually call delta x, or the length of the interval, b minus a, cut into 1, 2, 3, dot, 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 up to n slices. So this is still the same as it is in Calc 1. But each slab is going to have a different cross-sectional area, right? This is not turning out to be a very good-looking cow. But the idea is, right, like if you cut the cow in different spots, you're going to get different shaped steaks. Don't tell my vegan wife I said that or used that analogy. Let me erase that too so no one's horrified by that when they see it later. And so, as we go through this volume and we slice it, each slab is going to have a slightly different cross-sectional area. And so that's really going to be the key to doing this. So the volume of the ith slab, since it's a cylinder, is going to be easy to calculate. It's going to be that cross-sectional area, AI, times the thickness, delta x. And this is from the old school volume formula. Volume equals area of the base times height. It just so happens that our height is sideways and the area of our base is not a circle, right? So anyway, The key to these problems, though, is going to be determining that a sub I, determining a formula for this a sub I, and in this case, a sub I is a function of x, its location on the x-axis. So what we want to do is, even though these all have different shapes, we want to boil everything down to location on the x-axis. If we're going to slice perpendicular, then we want everything about this slab to be relative to where it's located. So what I want to find is, I want to find its location. I know the thickness is going to be some kind of delta x, but now I need to find a formula for this cross-sectional area depending upon my location. And so that's what I mean by a of x here is determined at each slice location, x sub I. Going through the rest of this is some pretty straightforward calculus from Calc 1. We have the volume total is approximately, not equal to, but approximately the sum of all those slabs, or the sum of each slab. Now, the actual volume total is going to be the limit as n approaches infinity of all those slabs. And so eventually what's going to happen is those thick slabs are going to get thinner and thinner and thinner, and you're going to have like so many of them, and eventually you're going to get the total volume of this solid as you go, as n approaches infinity and your slices get thinner and thinner. And that is, by definition, a definite integral. And this turns out to become the integral from x equals a to x equals b of the cross-sectional area ax integrated with respect to x, where a of x is the cross-sectional area perpendicular to the x-axis. And the key here is you must find a formula for a of x, right? So let's highlight our little formula. This is our working formula, and it's important that you understand what a of x is. Now, as I said before, you can do this one of two ways. You can cut it perpendicular to the x-axis, or you can cut it perpendicular to the y-axis, and you're really going to get the same scenario, right? What's going on is you have this blob here, blob, blah, 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 and you are going to slice it now, not perpendicular to the x-axis, but whoosh, 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 perpendicular to the y-axis, and then each one of those irregular shapes, like this one in the middle, is going to become approximated by a cylinder. That's the approximating cylinder in there. And then what you're going to do is you're going to say, well, this time, since I'm slicing it perpendicular to the y-axis, the thickness is going to be delta y, and this cross-sectional area I got to find, that's going to be an actual function of y this time. And then the rest of it is the same. The volume is approximately the sum of all those slabs, which is the base times the thickness. And then if you want the volume total, it will be actually equal to that sum if you take the limit as n goes into infinity, and it will then become the definite integral from c to d, where c is the lower limit with respect to y and d is the upper limit with respect to y, of all those cross-sectional slabs integrated with respect to y, where ay is the cross-sectional area perpendicular to the y-axis. So, a couple things that I want to say. In the next video, we're going to look at some examples. But I am very much interested in you doing this setup carefully. I really want you to make sure that this is correct before you move on. In fact, the numerical answer you get at the end of this, whatever this is equal to, right, is going to be worth less to me than the setup in this section. In this section, the integration is pretty straightforward. It's not a whole lot of crazy substitution that you have to do. So you really want to focus on your setup. And you guys aspiring to be engineers, you really want to take the time to look at the architecture of this, because when you go out in the real world, you're going to have to describe your solid in AutoCAD or to another person. And you're going to have to use mathematics to do that. So you really want to take the time to learn this setup. Okay. Anyway, in the next video, we'll look at some examples.